Morning, everyone. I'd like to thank the organizers for giving me the opportunity to speak. I'm a PhD student from the University of São Paulo, and in fact, what I do is set theoretic topology. And this talk is about some applications of cardinal problems regarding compact-like properties in hyperspace. Okay, so first I will introduce the concept of the hyperspace of Vietoris. Then I will introduce the compactness, where A stands for a set of free ultrafilters. Then I will talk about some lemmas that are useful, and finally I will talk about some of our results. Okay, so given a topological space X, one defines cell X as the set of all closed non-empty subsets of X. And then given a subset of X, we define U plus as the set of all elements of cell X which are contained in U, and U minus as the set of all elements of cell X which intersects U. And the Vietoris topology on cell X is the topology generated by the sets of the form U plus and where U is an open subset of X. Okay, so this generates a topology on cell X, and this is what we call the Vietoris hyperspace of X. And let's talk about some of the properties of the Vietoris hyperspace. Well, the topological properties of cell X highly depends on the topological properties of X. And I will list some of the most simple properties. I think that this is where the concept of the Vietoris of hyperspace had its origin. And if X is a compact metric space, so X has the topology generated by the Hausdorff's metric, which is the natural way to measure the distance between two compact spaces in a metric space. So X is always T0, even if X is not. If X is T1, so is cell X. And now for the rest of this talk, let's suppose X is T1, okay? X is a regular space if and only if cell X is Hausdorff. And the following are equivalent. X is normal, cell X is regular, and cell X is a type of space. Now let's start to take a look where things get interesting. If X is compact, then cell X is compact and the converse holds. This theorem is due to Vietoris. And when topologists look at this, what we want to ask is if we can replace compactness by some compactness-like property, like compactness, paracompactness, and so on. So let's ask a general question. Do you have water, please? Oh, thanks. Thanks. So let's ask a general question. Are there such theorems for generalizations of the notion of compactness? I mean, can we replace compact by pseudocompact, by countable compact, or something like that? In this talk, we will focus on pseudocompactness and its generalizations. So now we follow the notation of Ginsburg. Okay, there are two main notions of pseudocompactness, which is the classical one, which states that X is pseudocompact if and only if every continuous function on R is bounded. And there is this other notion of pseudocompactness, which states that every sequence of non-empty open sets has an accumulation point. For Tikhonov space, they are the same, they are equivalent. And there is more. For Tikhonov spaces, they are the same for its hyperspace. So COX is not always Tikhonov. In fact, as I said in the previous slide, X must be normal in order to COX to be Tikhonov. So it's not something that happens every time. But if X is Tikhonov, these two notions are equivalent for their hyperspace. Okay, so let's start to talk about what happens if we replace compactness by other things. So Ginsburg, in the same article, has proved that if COX is countable compact, so is every finite power of X. And there's some kind of converse here, which states that if every power of X is countable compact, so is COX. Now, what happens if we talk about pseudocompactness? If COX is pseudocompact, so is every finite power of X. The same of what happens with countable compactness. And Ginsburg asked if this converse also held when we considered pseudocompactness. Now recall that if x to omega is pseudocompact, then every power of x is pseudocompact. So what he asked is if when we replace countable compactness with pseudocompactness, okay? And Michael Rushak has answered this question. He showed that there exists a subspace x of beta omega such that x to omega is pseudocompact, but COX is not pseudocompact. So this answer is false, okay? And myself, along with Yasser Ortiz Castillo and Artur Tomita, have provided another example of a subspace x of beta omega such that x to kappa is countable compact for every kappa lesser than h, but COX is not pseudocompact. So here's another question, since the answer to this question is false. How to further characterize the pseudocompactness of COX? And we noticed that the cardinal characteristics of the continuum kind of plays some role here. So in order to talk about this, we will introduce a generalization of pseudocompactness due to Salvador Garcia Ferreira. And we define it as follows. So given a topological space X, a set of ultrafilters, and a cardinal kappa, we say that X is kappa A pseudocompact if and only if every family of kappa sequence of open sets there exists a single P in A that such that for every alpha, let's say a P limit for the sequence associated to alpha. So you must, in order for it to be kappa A pseudocompact, you must have a single ultrafilter that gives you accumulation points for every sequence at the same time. So there are some obvious properties here. If A is a subset of B, and both are a set of ultrafilters, if X is kappa A pseudocompact, it's also kappa B pseudocompact. And if it is lambda A pseudocompact for some lambda, and you pick a cardinal lesser than lambda, it's also kappa A pseudocompact. And for every cardinal lesser or equal to omega, so kappa is a finite cardinal or omega, X to kappa is G pseudocompact if and only if X is kappa omega star pseudocompact. So, but the same does not hold omega. Now, let's talk about what's going on here. You may want to talk about the, let us say, degree of pseudocompactness of a topological space by asking if its kappa power is pseudocompact. But if kappa to omega is pseudocompact, then every power is pseudocompact. So this is not a good way to measure the degree of pseudocompactness of a topological space. And kappa A pseudocompact generalizes the concept of pseudocompactness and plays this role very well. So we are going to use kappa A pseudocompactness or kappa omega star pseudocompactness in order to talk about our results. So here are some lemmas which we will talk about. Given a topological space X and a subset of X, we say that A is relatively countable compact if and only if every infinite subset of A has an accumulation point in X. So the accumulation point is not in A, it's in X. That's why it's relatively countable compact with respect to X, and it's not, let us say, absolute countable compact. Okay, so if you have an open, discrete, and dense subset of X, and D to kappa is relatively countable compact, then X to kappa is pseudocompact. Okay, so this is a way to talk about pseudocompactness. And sorry, what I want, I think there's a mistake here. This is also true, but what I wanted to say is that if D to kappa is relatively countable compact, then X is kappa omega star pseudocompact. And the converse also holds. Okay. And when we talk about the hyperspace of X, it is pseudocompact if and only if every sequence of pairwise disjoint elements. Oh, I forgot to write what's Z. Okay, so E is the set of all finite subsets of D, which are closed. Okay, so it's a subspace of cell X, and cell X is pseudocompact if and only if every sequence of pairwise disjoint elements of E has an accumulation point in cell X. Okay, so now let's talk about some of the results we have achieved. And if there is enough time, I will sketch a proof of these results. Okay, so if X is a topological space between omega and beta omega, then if it is C omega star pseudocompact, COX is pseudocompact. So there was no kind of converse, if COX is pseudocompact, then every finite power of X is pseudocompact. But there is no implication to this other side, and this is some kind of implication, okay? And this is in some way the best result you can achieve, because if you assume that C is regular and that there exists same comparable selective ultrafilters in Kessler order, then there exists a subspace of beta omega such that omega to alpha is relatively countable compact for in X alpha for every alpha lesser than C. So it is alpha omega star pseudocompact, but COX is not pseudocompact. Okay, so this is kind of the best result in this sense you may achieve. Now, if you have a subspace of beta omega which contains omega such that COX is pseudocompact, then X is kappa omega star pseudocompact for every kappa lesser than PRA. And also, COX is kappa omega star pseudocompact for every kappa lesser than H. We try to go higher on the diagrams, but those were the best results we could achieve. Maybe it works with B, but I'm not sure. Okay. And as a corollary, then for every subspace of beta omega which contains omega, if COX is pseudocompact, then all powers of both X and COX are pseudocompact. So how do we prove these results? I will talk about another result, but our main tool, our main topological tool for which we developed to prove these results was this lemma. If between omega and beta omega, and if P is a free ultrafilter over omega, and Cn is a sequence of finite pairwise disjoint non-empty subsets of omega, and G is the set of the choice functions of this family, and Zp is the set of the P limits, ultrafilter limits of the elements of G, then the following statements are equivalent. The sequence has a P-limit point, Zp is contained in X, and the closure of Zp is the P-limit of Cn. So what's going on here is the sequence has a P-limit if and only if Zp is contained in X. So what we must do in order to make COX pseudocompact is to, for each sequence of finite pairwise disjoint non-empty subsets of omega, include in the space X the set Zp for some free ultrafilter P. And in order to destroy the pseudocompactness of COX, we must fix a sequence and destroy all the ZPs for every free ultrafilter P. So this is the theorem I would like to talk about a bit more if there is not enough time. 5 minutes. Okay. Okay, so we broke down this theorem in the topological part and the combinatorial part. And the topological part states that if theta is an infinite cardinal and you have a family of infinite subsets of omega of cardinality lesser than theta, and such that for every sequence of finite non-empty pairwise disjoint subsets of omega, there exists an infinite subset of omega E and an element B of this family, for which the intersection of B with the union of the CNs with N in E is finite. Then there exists a topological space X between omega and beta omega, for which so X is pseudocompact and X is not theta omega star pseudocompact. So we used theta equaling B and produced this example. There exists a space X between omega and beta omega, such that so X is pseudocompact and X is not B omega star pseudocompact. So the question we are trying to answer here is, we know that if so X is pseudocompact, then for every cardinal kappa between lesser than H, X will be kappa omega star pseudocompact. Okay, I'm talking about this result. I'm sorry, not H, PIR. So the thing is, how up can you go in the diagrams, or how down can you go to look to it by the other side? And this is a ZFC theorem that states that it doesn't work for B. So the strategy to prove the first theorem is to construct X by using transfinite recursion. We enumerate all sequences of pairwise disjoint finite non-empty subsets of omega, write down their sets of choice functions, and choose some bijections between the elements of A and omega. Then we start by setting x0 equaling omega and start defining some blocks of the space. So for each alpha lesser than C, we will include some ultrafilter limits for some Q alpha. And in order to choose the Q alpha, we must leave out of the space some things that will guarantee that the space will not be theta omega star pseudocompact. So I think that there's not enough time to go into details here. Then we apply this theorem by using theta equaling B. You must use an unbounded family of cardinality B You may choose the functions should be strictly increasing, and you use the images of the functions. So if C is a sequence of pairwise disjoint finite non-empty subsets of omega, you pick this function, define it like this, and define this set N. You use the fact that B is unbounded to pick a function which dominates F and define this set N, okay? So you define the set E as the set of all N's that have empty intersection with G omega. And what you show is that the set E is infinite. It's a simple calculation here, okay? So you get this empty intersection and the proof is complete. Okay, so this work is published in Topology and Applications this month. And I think I'm done. And thanks for your attention.